Okay, so the recording is now set up. We can start. As usual, if you have any questions midway, you can always stop me and ask. Don't use the chat because I'm not able to look at the chat while I'm presenting. Simply put on your mic and speak. So if you have a group G, we can define the following as a group algebra. So this is a bit abstract, so you have to keep an open mind for it to make sense. If we have G, a finite group G, and we know the elements to be G1, it has a total of n elements, which we call G1, G2, all the way up to Gn. And as usual, we need a field that is either the real or the complex numbers. So we simply define elements of Fg we create a set Fg, which we define as this. We simply multiply any element of Fg will look like this. You multiply scalars from the field and the elements in the group. So the elements in the group behave like a basis of a vector space. So any element in Fg is simply written as a linear combination of these group elements. And since they are finite, you can use all of them. Of course, some of the coefficients can be zero, if you like, and so on. So any element in Fg will look like this, and then G1 up to Gn behave like the basis. So if you pick two elements, say U and V from Fg, you can define addition by simply adding the coefficients. That gives you the addition. And you can define a scalar multiple by simply multiplying the scalar, each of the scalars by this scalar lambda. So now we have been able to define vector addition and scalar multiplication. And under these operations, this set Fg, where each element looks like this, will form a vector space. You can check that it satisfies all the properties of a vector space, but what was important is that we're able to define the vector addition and scalar multiplication in the set. And also we have clearly defined what the element looks like. It looks like this. So Fg, we have agreed now, this is a vector space over F, and the dimension is n. N is precisely the number of elements in the group G. And this set G1 usually will retain the order. We have to order the basis, because if you change the order, you get the wrong elements. So I mean, at some point you need to keep track of coordinates. So if you reorder the basis, you get different coordinates. Maybe not the wrong elements, but you get different coordinates. So we have to retain the order at some point. And we call these elements of the group the natural basis of our vector space, Fg. I hope that makes sense. So it's just an abstract definition where you define your vectors as elements that look like this. So you get new elements or you get new vectors by changing the coefficients in this linear combination. Hello, you can hear me?
Yes.
Okay. So we proceed. Let's give an example. Here is a group with exactly 3 elements. We use E for the identity element of the group. So we can define the vector space CG. So we pick the field to be the complex numbers to define this vector space CG. It contains elements that look like this. These are examples of elements that appear in this set CG. So you simply pick all the elements of the cyclic group of 3 elements, and you order them as E, A, and A squared. If you pick that to be an order, then elements in CG will be linear combinations of these group elements. So if you want a new element, you can change the coefficients, you'll get a new element. So we have picked 2 elements here, V and U. For V, coefficient of E is 1, the coefficient of A is -1, and that of A squared is 2. So V is equal to half E plus 5A. The second one, the coefficient of A squared is 0, so A squared is left out. And you can add them using the same operations that we defined earlier. So to add them, you simply add the coefficients. 1 plus a half minus 1 plus 5 will give us 4, and then A squared is 2 plus. This should be A squared, not U squared. If you multiply U by a third, you simply multiply every coefficient by a third. That's how you set up the. So this gives you 2 possible elements of CG. So we have another way of rewriting this. So instead of labeling or rather putting subscripts to the elements, instead of writing them as G1, G2, or Gn, you simply write this element of Fg as a linear combination, but you write the coefficients with the element itself as a subscript, so that lambda subscript G, this lambda subscript G is the coefficient of G, and it runs through all the elements in G. So that way you don't have to worry about the numbering of the elements in the group. So we can use a product in G as follows to define the multiplication in Fg. The reason now here you can multiply vectors is because already the elements from G have their natural group product defined. So you can define, here we have 2 vectors and you're able to multiply them because you're using the multiplication, the natural multiplication already existing in the group G. Usually you would not be able to multiply vectors in an ordinary vector space, but this one has an extra structure and you can define multiplication. So you can multiply elements in Fg exactly as it appears here. So simply multiply the coefficients and the corresponding elements as well. So you could choose to relabel the elements if you take, because if you can represent every element okay, there's something I can't quite remember here, but you can rearrange this. You can rearrange these coefficients so that you rewrite them like this. You still end up with the same thing. You can try it with a small group where you rewrite. If you have a group with only 3 elements, it's possible to rewrite these elements in this form, and you see that you end up with the same sum for both cases. For both this and this, they give you the same, exactly the same sum for the same vector. These 2 representations here. I think that is fine. So you can check this later. I will also try to write out the expansion. If G is equal to C3, we have UV and CG in the one we picked up earlier. If you multiply them, you will end up with this. So we can go back to U and V in the previous example. Simply multiply all the corresponding coefficients and you add them. So for instance, if you want to get the coefficients of E, you look at all situations where you get the identity. So what is U and V? So we have one possible is a half, where you have this E and E. E and E will give you E when you multiply them. So a half is one of the possibilities. Then the other one is what? You have negative A. You have A and 5A. No. We have 2A squared here and 5A. A cubed will give you the identity. So 2 and 5 will be 10. Is that correct? So we have 10 and a half. Is that correct? To get you the coefficient of E after all the multiplication is done, which should be 21 over 2. You can see how that is working out. You need to speak a bit. It's difficult for me to tell whether you are together or not if you are not speaking. At least try to answer the question. Whether yes or no would be sufficient. Okay, so we continue. So that's how you do the multiplication. You can use the same ideas to get the coefficients of A and A squared by running through all the multiplications and using the multiplication in the group to work out this. Can you hear me? Is everybody in this room?
Hello.
Your voice is poor.
Your audio is very poor. We can't hear you.
Yeah, it was. It was okay. Poor.
We can't hear you.
Can you hear me now?
Yes, better now.
Yeah.
Maybe it's my microphone.
It was appearing that you are walking.
Start that again.
Fine, I'll leave the microphone. I'll just use the one directly on the computer. Now you should be able to hear me clearly.
Yes.
So do I proceed from where I am, or where do I start from?
Just where you are.
Just proceed from there.
Okay. Yeah, but if you notice that the voice is not clear, you should inform me earlier. The reason for that is maybe now the previous section, the recording will not be clear. If you want to watch it again, it may not be clear. But I believe it's not a very long section, so you'll be fine. So this is how you define the multiplication. So the vector space, once you have the vector space Fg, and in addition you're able to define vector multiplication, then we call this Fg the group algebra. So, and the identity in the group algebra, we can define the identity as just the identity element in the group, because if you multiply any element in the group by the identity, every element will be left unchanged. So this the vector that would be like the identity in the group will be this element 1e, or just e. You don't need to write the 1. E is enough, where 1 is supposed to be a scalar and e is the vector. So you notice now we are using this element e to represent the identity in the group, and 1 to represent the identity in the field, or the unit element in the field. So when there is no confusion, we shall just write this identity element as 1, the element of the algebra. So take note of the algebra. In the algebra, the multiplication is this, and the identity would be denoted as just 1. So you can check that all these properties are satisfied in Fg. Multiplication in Fg. Remember, there's a difference between the scalar multiplication and multiplication in Fg. Multiplication in Fg, we already defined it. Scalar multiplication simply means you pick an element in Fg multiplied by a scalar. But the multiplication here we are talking about is multiplying two elements in Fg, the algebra itself. So you can check these properties. It should be easy for you to check that all these properties will be satisfied for elements in Fg. So the zero vector will be simply 0 multiplied by any other vector. The proof, again, it's simply some properties you need to look at, and I think on your own time you can check them and confirm that this works. So just to be clear, the multiplication we are talking about is this. So this is this would be an element R, and this would be another element S. So you're multiplying elements like this and show that they satisfy all the 7 properties. Now, based on this, we can now define the regular Fg module using Fg as our vector space. So if we pick this Fg as our vector space of dimension n over f, where n is simply the number of elements in the group G, then we can pick any 2 elements in the vector space V. So u and v will be elements from this Fg, and lambda will be a scalar from the field. We pick any 2 other elements, G and H in G. We can define multiplication as Vg, trying to define an Fg module. So we need to define a multiplication that will work. So if you pick V from Fg, you can simply multiply it by G, an element from the group, and you will still get an element in the vector space using the natural multiplication that was defined earlier. And we've seen through the properties that the multiplication is associative. So you can have that property satisfied. If you multiply it by 1, it doesn't change. And the scalar multiplication also, the scalar can jump out of the brackets. And it's linear. So you could go back and check. There's a previous proposition which based on these properties, you can show that now this FG will be an FG module. V now will be an FG module under this multiplication defined like this. So here we have a definition. I hope this is clear how this multiplication is defined to turn this vector space into an FG module. So it is called FG, but it's also this FG is an FG module based on the definition of an FG module we gave earlier. You can still hear me, I hope.
Yes.
At least now I'm getting response, so it means the audio is good. So here's we are defining the regular FG module now. So if G is a finite group and F is R or C, you can, this vector space FG as we defined it earlier with the natural multiplication VG is called the regular FG module. So that gives us the FG module,
Yes.
regular FG module. So again, you can set up this representation. We agreed that this map, which takes an element G to the matrix of endomorphism induced by G with respect to a given basis. In this case, we are using natural basis. Will be called the regular representation of G over F. So you can work out the matrices for each of the elements for a fixed basis. The basis here is fixed anyway. Once you work out the matrix of representation, then you have and then you create this representation which maps G to the corresponding matrix. You end up with a representation which is called the regular representation of G over F. So this is another way of defining a representation, of constructing a representation. We have seen a few earlier ways, and this is another way of constructing a representation. The regular FG module will have dimension equal to G. So you should be able to check that the regular FG module is faithful. I think I will. It's a 2-line proof. It's already in there. You can check it in your own time. Here is an example. Again, we use a cyclic group of order 3. So looking at it carefully, we see that elements we can be able to write the elements in this form of the FG, the vector space FG. It will have elements that look like this. Now we can So the basis will be A squared. That will be the basis of our vector space, right? So if we pick any vector and multiply it by E, so any vector in the space, if you multiply it by E, what happens is you end up with the same vector space. So the matrix here, with respect that is this is just identity matrix because this is not chained. This what do you call it? This vector is mapped to itself under this endomorphism induced by the identity. So this will give you the identity map. Every vector is mapped to itself, and the matrix here will be the identity matrix. Now, if you pick any other vector, again, and let it act on A, so what happens is there's a switch. So A, if you multiply A by E, you have lambda 1A. So that's why you have lambda 1A here. If you multiply A and A squared, you have lambda 2E. No, you have lambda 2A squared. That's why we have lambda 2A squared here. And you know that A and A squared will give you A cubed. And we know from our definition up here, A cubed is E. So the lambda 3 will be the coefficient of E. So you can see here what happens. This vector is mapped to a different vector, but the same coefficients, but rearranged. So if you want to get the matrix of representation, you just need to find a matrix that will convert this vector lambda 1, lambda 2, lambda 3 into the vector lambda 3, lambda 1, lambda 2. And that is just a permutation matrix. You permute permutation matrix where you just interchange the elements in the, you switch the elements in the, the rows in the identity matrix, and you will get the matrix that does this. So I think I may have done that at the bottom. So the matrix at this point would be this one. Just switch the identities. So try to, if you want to see what I mean, pick these coordinates, lambda 1, lambda 2, and lambda 3. If you multiply by this matrix, you should get the new vector lambda 3, lambda 1, and lambda 2. So that's how you know this is a correct matrix. By now, I'm assuming you have had a chance to look at the matrix for a linear transformation. So hopefully what I'm saying is making sense. Because the matrix is supposed to act on the coordinates of a vector. So the same way here, you have A squared. This lambda 1, lambda 2, and lambda 3 is mapped onto lambda 2, lambda 3, lambda 1. So lambda 2, lambda 3, lambda 1. If you want to know if your matrix is correct, simply pick these coordinates, lambda 1, lambda 2, and lambda 3 as a vector. In this case, in our case, we are multiplying, our vectors are raw vectors. So you actually have to multiply the vector on the left. Multiply the vector on the left, because this book, as a convention, has been using the vectors, writing the vectors as raw vectors. So our multiplication will be on the left. Is that making sense? Hey, gentlemen.
Yes.
Mmekula lunch mzito bana. Okay. So that's an example. And now this will be a representation where E is mapped onto this matrix, A is mapped onto this matrix, and A squared is mapped onto that matrix. So if we pick any other FG module, V, And then we pick an element from the set FG. Remember how we define the set FG? So mu G. So you can define the multiplication of VR as follows: mu G, write it as mu G, and then VG. So this VG is a multiplication in this VG is a multiplication in this first FG module. It's different from the multiplication in the regular FG module. So this is just any other module, and this is the regular FG module, FG, right? So we let FG act on this V. All we do is simply pick, you pick the coefficient, each, just pick the coefficients only and multiply the group element with that coefficient by V. And now this multiplication is the one in this FG module. So we define our multiplication by that. So this defines an action of FG on an FG module that allows us to have an element VR of V. So you realize that VG will be an element in the FG module, and therefore a sum of the elements, or rather a linear combination of the elements in V will also be an element in V. That's why this action on FG allows us to have an element VR of V for all R in the group algebra FG. So I hope this makes sense as well. What follows are just some examples of so here is an example. I think we just need we have a permutation module. The permutation module we had in the early example, I think it's given example 4.9 as V1, V2, and V3 with a basis. So we define the multiplication on the basis elements with an element R in the what do we call it, in the regular FG module. So this would be the regular FG module, where G is I think you take G to be S4, right? The group is S4. We define FG, so this will be vectors in FG, the regular FG module, and then pick any vector from this permutation module basis. So V1R will be simply given by this. Now, under that example, V1 multiplied by a permutation simply sends V1 to V, and the subscript will be the subscript where the permutation sends 1. So 1 goes to 2. So V1 under this 1, 2 will take V1 to V2 as seen here. And since you're multiplying by V1 throughout, we also multiply this by V1. And here V1 will be sent, 1 will be sent to 3. So V1 goes to 3. That's how you do the multiplication. You can do the same for V2R. And you will see that V2R will go to lambda 1 V1 plus mu V2. If you want to do it for a sum, 2V1 plus V2 multiplied by R, this is what you end up with. You can I think you can see that. So this is just an example to illustrate how the computations are done. You probably need to spend a little more time on it, unless you have questions on it. Is it making sense? Yes, Benson.
Yes. Yeah, it's making sense.
So can I assume you're the spokesman, or the others will speak for themselves?
Maybe I be the spokesman or someone to say the other
You don't want to
question.
claim.
Yes.
You don't want to claim the position.
Yeah.
Okay, so if V is a regular FG module, then for any vector in V and R in FG, the element VR is simply the product of V and R. So the FG module can act on itself, right? It can act on any other module, or it can act on itself because it's also an FG module. So here it gives a list of properties that are true for this any FG module and the regular FG module acting on this FG module. So again, these are properties you can check on your own. So that finishes the what we needed to do on FG modules. So now I hope you have gotten the essence of that. We've learned about the FG module, and we've seen how the FG module, we've done about the FG, the set FG as a vector space, and how we convert it into an FG module, and then how we were able to define a group algebra, and also how we have gotten how the FG module can act on another. The regular FG module can act on another FG module. Try to look at that and see if you have any questions later. If you have any questions, we can look at them. So what I would like to propose is we move on to the next topic, and that is FG homomorphisms. Is that okay?
Yes. Yes.
Okay, so I'll stop sharing this and get to the next. So you will have to confirm if you are seeing my screen again. Maybe William can speak now. Can you see my screen?
Yes.
William has been quiet today.
Yes, I can see the screen.
Oh, your audio is, your microphone is a bit breaking.
You
But
can't hear me.
I can hear you now.
Yes. Okay. Yeah, I can see clearly.
So here's a definition. So again, William, I assume you are the spokesman. So the others agree with you. They agree with you that they can see.
It's all right. All right.
Yes, you are the official spokesperson. Now, for seeing the screen. So let's define an FG homomorphism. So let V and W be two FG modules. So we now want to see how we can relate two FG modules. So we define a function from V to W, and we say it's an FG homomorphism if the function theta is a linear transformation, and not only is it a linear transformation, it also preserves this multiplication for all G. In other words, theta Vg is the same as the image of V multiplied by G. So remember, this multiplication on this end is a multiplication in this FG module, and here Vg, the one on the inside here, is a multiplication that is defined on this V as the FG module. So there are two different multiplications running here. There's one here, which comes from this FG module. Now theta V is a vector in W, so this theta Vg would be the multiplication from this W as an FG module. You can see that? So it's basically a linear transformation, but more over and above the linear transformation, it must preserve this multiplication. So if we have a finite group and we have theta from V to W defined as an FG homomorphism, if you pick any V in V and R in the regular FG module, then we can define theta VR to be equal to theta VR. So remember, VR is just remember the multiplication we defined earlier, where FG acts on an FG module. The set FG acts on an FG module. So VR's theta, if okay, here I think I was going back to the notation in the book where he puts the function on the, I lost track here. I was trying to stick to this notation, but here they got the better of me. This theta should be on the left-hand side by our notation. In the book, they put it on the right-hand side, but I've avoided that notation so that we can stick to the usual notation that we used for functions that we're used to. So you can, this theta should move to the left-hand side, right? So So this is best. I think this should be clear. This calculation should be clear. You just follow. Use this as your R, then apply V on it and assume this kind of multiplication. You already know that this theta is an FG homomorphism. So give me just 1 minute. I'll be back. Okay, so I'm back again. Poleni. So so use the fact that theta is already an FG homomorphism, and multiplication will be defined like that. But now you are picking now instead of just G, you're using R, which is a linear combination of all these elements in the regular FG module. So instead of having only one G, you have a sum, a linear combination of them. When you work out that multiplication, this is what you end up with. And it shows that so this is a map from I think it's fine. It basically shows that this map also preserves this multiplication. So like I said, this theta needs to move to the left-hand side so that it is the same as the others. So here it's theta acting on V. So ideally, if you were to follow the usual notation, this should be theta with V in brackets, and this should be theta with V in brackets as well, like that. Are we together?
Yes.
So the next one says, let V and W be FG modules, and let theta from V to W be an FG homomorphism. Then the kernel of theta is an FG submodule of V, and the image of theta is an FG submodule of W. I don't know if you can understand that. I don't know if Google Meet has a blackboard of some sort. So let's first go through the proposition. I think it has a whiteboard, but I've never used it. Let me see if we can use it in a minute. So we have V and W, the FG modules, and we define an FG homomorphism from V to W. So the kernel of theta, you're familiar with the kernel of a linear transformation. So the kernel will be a subset of V, and we say it will be a submodule of V, and the image will be a subset of W, and we claim that the image will be a submodule of W. I don't think I need a diagram. I think that will be fine. We can just move to the... Now we automatically know that the kernel is a subspace of V. That is one requirement for a subset to be a submodule. It must first be a subspace. We also know that the image of theta is a subspace of W. That's from linear algebra now. If we pick any vector in the kernel, theta, we need to check that this multiplication is preserved. So theta of Vg would be equal to theta of Vg. But now theta V is in the kernel, so theta acting on V will give you the 0 vector, and 0g will be equal to 0. So it means this vector Vg is still in the kernel because it has been mapped to the 0 vector. The kernel is simply the set of all vectors that are mapped onto 0. And we have shown that Vg is still mapped onto 0. So Vg will still be in the kernel. And therefore, this second property now qualifies the kernel of theta to be an FG submodule. Of V. Sorry, this should not be kernel theta. This should be V. So this should be removed. This should be an FG submodule of V, not kernel theta. The kernel theta is a submodule itself. V is a vector space, a capital V. The second case is to check that the image also is a submodule. So I think this also again is self-explanatory. If W is in the image of theta, it means there must be some element in V which is mapped onto W. And we can check this multiplication. WG can be written as theta V G. And theta V is definitely a vector in V. And sorry, theta V is a vector in W. Oh, no, it's fine. Under this theta Vg, we can set this to be theta Vg. So we've been able to find a pre-image. The pre-image of Wg is just Vg, right? We've been able to find a pre-image for Wg, and that is Vg. So Wg is definitely in the image of theta. The reason we can call this a pre-image is because of this property up here. We know that theta Vg is the same as theta of into brackets Vg. So image theta is an FG submodule of W and the kernel as well. I take time to go through these proofs to understand them fully. So examples again. So we have a trivial case here where we have a map from V to W where every element in V is mapped onto 0. And this is a homomorphism. It's an FG homomorphism rather. And here, since the whole of V is mapped onto 0, then the kernel is the whole of V. I think that should be obvious. It's just the trivial homomorphism. is an FG homomorphism. So here we pick a scalar from the field and define a map from a vector, an FG module rather to itself by theta v is equal to lambda v. So this scalar is fixed. You simply map each vector in V to its scalar multiple, lambda. So lambda is fixed. And pick every vector, send it to lambda times the same vector. So it's easy for you to check that this will be a linear transformation, first of all, and therefore is an FG homomorphism. You can check that it's an FG. You can also check that it's an FG homomorphism because then you check that theta, take theta of VG, put VG in brackets, it will be the same as lambda VG, but now lambda also can be put outside the brackets. Then you will end up with theta of VG. You can put this lambda V in brackets and put the G outside, but lambda V is just a theta of V, the same as theta of V multiplied by G. So the multiplication is also preserved. And this turns out to be an FG homomorphism. So your work is to prove this. Write the details of this completely. We have the map. First of all, prove that this map is a linear transformation. Once you know that's a linear transformation, confirm that it's an FG homomorphism, where show that it preserves the multiplication. So there is another example here. It picks G to be a subgroup of Sn. So G is a permutation group. Any subgroup of Sn is normally called a permutation group.
Just a minute.
Yes.
You said to prove that the map is a linear transformation. Are you sure that it preserves?
It's simple.
I was writing.
You need to prove that's a linear transformation and also show that's an FG homomorphism.
Okay.
So I was simply describing what it means to be an FG homomorphism, which is also in definition up there. So there's nothing much more to it than that. Are we together?
Yeah. Yeah.
So this map is an FG homomorphism. Here's another example. The example here assumes that the span, we have an n-dimensional vector space. So V1 out Vn is the basis of V. And we define the permutation module for G over F with W is equal to span of W. Let's pick W to be equal to span of W to be the trivial FG module. So it's just a vector space spanned by one vector, one-dimensional vector space. So we define theta from V to V as follows. So W is fixed. And we pick any vector in V and we send it to this vector whose coefficient is simply the sum of the coefficients of this vector. The coefficients, the coordinates rather of this vector V. So this one is a vector in V because it's written as a linear combination of a basis elements. You simply pick the coordinates and add them. They become the coefficients of W. So this is a one-dimensional vector space on this end, and any this will just be a multiple of W, so it will still be in this capital W. So we define the map as this. Now we define this multiplication. Theta of VG is equal to the same as, again, you sum all these things, WG. Now remember, this is a trivial FG module, so WG will be equal to W, right? So you can replace WG with W and you end up with this. You can see that? So it's important, you should be able to check that this map is a linear map. This map from V to capital this should be W, not V. So the map from V to W, you can confirm that it's a linear transformation and also check that it is a linear, it's an FG homomorphism. So what is in, so that's work for you to do again. Check that this map here is a linear transformation and confirm that it's an FG homomorphism under this definition of the multiplication. Now, now theta is an FG homomorphism, and we can find the kernel. The kernel is a set of all elements which are mapped onto 0. So the 0 vector on this side will only be obtained if these coefficients sum up to 0. So the kernel of theta will simply be consisting of all those vectors whose coordinates add up to 0. The map is surjective because if you pick any you should be able to see that the map is surjective. Every element in W will okay, give me a minute again. So are we, I hope you have had some chance to analyze this and see that it's a linear transformation and that it's an FG homomorphism as well. Are we together? Can you see the argument which will help you see that the image is the whole of W, capital W? So what you can do is you write it out in full. Then I can have a look at what you've written down. Are we together? It's not really an assignment, it's just for you to expand your knowledge or at least show off your knowledge now. So And then that also helps you know whether you are able to, you have understood. You can hear me?
Yes.
Okay. So here we now talk about isomorphic FG modules. So an FG homomorphism is said to be an isomorphism if theta is invertible. In other words, the inverse of a map exists. The other way to say this is the map should be bijective. If you have one-to-one and onto map from V to W, which is linear, it's an FG homomorphism. Then it becomes an isomorphism. If V and W are said to be isomorphic, if there exists an isomorphism between them. So this is the notation for, I think it's usually just one line. I don't know why I put two. It's usually just one line. Yeah, not these two. One line and this thing that looks like a worm. So here's a proposition which says that if theta is an FG isomorphism, then the inverse will also be an FG isomorphism. Not just an isomorphism, but an FG isomorphism. So we can take, here you just need to recall the properties of theta inverse. The inverse of theta. So the inverse acts on vectors in W and sends them back to V, right? So theta inverse acting on W, G, again, I put this theta on the wrong side. I think I used the notation in the book here. And switched back to my notation down here. So this theta should be on the what do you call it? The left-hand side, this theta inverse. Similarly, this theta should be on this side. I think the next line says it properly. Ignore this first line. So we have theta inverse WG is equal to theta. And since this is this is just a vector in V. Theta inverse W is a vector in V. And since theta is an FG homomorphism, it's possible to put my brackets here and let theta just act on the vector first, right? But now theta and theta inverse will give you the identity, and the identity acting on W will just be W. So this will be WG. But now W itself we know is WG I think I made some mistakes on this one, especially from the beginning. So, but anyway, this is what you end up with. Hence, theta inverse WG will be equal to theta inverse WG. The reason for that is this. This is an isomorphism. So if these two are equal, theta is equal to this, then these things in the middle here must be equal because theta is an isomorphism. So we can come to that conclusion So theta inverse WG is just like the identity acting on WG. That's why you can write this. And we also seen that it's the same as theta with theta inverse in the bracket, where theta inverse is acting on W and G. So this one is just based on the fact that theta and theta inverse gives you the identity, and therefore the identity acting on WG will just give you WG. So that's no problem. And then this conclusion is based on the fact that theta is an isomorphism and it's injective. So if it's injective, it means if these two statements are equal, then the arguments here must also be equal. That simply requires you to remember the definition of an injective function, nothing more. Then it will make sense. You can ignore this top part. This top part, ignore it completely. Just start from here. So now this last, we definitely know that theta inverse must be a linear transformation as well. If theta is a linear an isomorphism, then theta inverse will also be a linear transformation as well. So the only part here we have shown is that it's also an FG homomorphism. So here are some results which again, you can use your knowledge from vectors to prove if V and W, if theta is an isomorphism from V to W, FG isomorphism, then you can check the following. Check that the dimension of V will be equal to the dimension of W. Here, all you are using is the vector space properties. You don't even need the FG properties at all. The dimension of V and the dimension of W must be equal as long as this map is an isomorphism. Check the chapter that talks about vector spaces. That should enable you to prove this. It says if V is irreducible, then W must also be irreducible, and vice versa. So you need to go back and check what does it mean to say an irreducible module, and how that implies that the image is also irreducible, and if this is an isomorphism. So I can leave this as an exercise. You will hand this in. So note this down. This one you will have to do and hand in. So let's see if we can get the page number. It's just under the, I don't think the page is numbered. So it's isomorphic FG modules. And then there's just on the, where the topic begins, this last bit is what you need. So you write out these statements, you write out their proofs, and then you will share them with me. You can hear me?
Yeah.
Yeah, so this one you need to hand in.
Yeah.
This kit. I'm thinking we stop there for today. The next theorem is a long one. The proof is pretty long. But if you have the energy, we can continue.
I think we can stop there. The rest can agree.
Yeah, we can stop
agree
there.
with it. Okay.
You are in total agreement?
Yes.
Yes.
Na hakuna maswali?
Mass argument.
I need to stop recording. So are you finding the videos helpful at all?